Welcome back to our video series on what is up with quadratic sequences. I'm your host, George Arrington, and in this particular video, part 2, we're going to look at what I call the direct approach. Let's see what that's all about. So what is a quadratic sequence? Again, from last video, I said that a quadratic sequence differs from other types of sequences by saying it's defined as S sub n, and when I say S sub n, that's the particular element in the sequence, the particular number in the sequence, is given by an squared plus bn plus c. And the n's are given by 1, 2, 3, 4, 5, and so on. In the last video, I gave you an example of a quadratic sequence, in this case 5, 11, 23, 41, 65. And I said that the first element of the sequence, which would be called S sub 1, is 5. S sub 2 is 11. S sub 3 is 23. S sub 4 is 41. S sub 5 is 65. And we could keep going if you wanted to go further. It turns out, by the way, that for our problem, for this particular method of solving the problem, we will only need the first 3. And by the way, in the last video, we saw that this one was solved by using the coefficients 3, negative 3, and 5. So the equation became 3n squared minus 3n plus 5. Okay, so when we look at the equation above, this general equation for all quadratic sequences, we notice that we have 3 things that we don't know. We call these our 3 unknowns. And they are A, B, and C. The other things like n and S sub n are given to us already, so it's these 3 things, these A, B, and C, that we need to solve. Now, one of the key concepts that we learn in algebra, in high school algebra, is that if you have a certain number of variables, a certain number of unknowns, then we have to have the same number of independent equations in order to solve for those variables. So if you only have x and y, then you need 2 variables to solve for x and y. In this case, we have 3 variables, and so we need 3 equations. If you happen to have some complicated problem that had 10 variables, we would have to have 10 independent equations in order to solve it. That would be quite a difficult problem. But in this case, we only have 3. Okay. Now we get each equation by using the value for n, 1, 2, 3, and so on. And as I said in the last slide, you really only need the first 3 because we only need 3 equations. Okay, so let's see what those are. Okay, so the first equation, S sub 1, we're using n equals 1, is equal to a times n squared. Well, n is 1, so n squared is 1. So the first term there is a. B times 1 is just b. And c we haven't done anything to, so it's a plus b plus c. Now, S sub 1, we said, was the first element in our sequence. So if you look at this sequence, we can see that the first element in that sequence is 5. So there's our first equation. A plus b plus c is equal to 5. Okay, let's go on. The second equation, S sub 2 is equal to, well, n is equal to 2. So we go up to the equation, we say n squared, which would be 2 squared. 2 times 2 is 4. So 4 times a is 4a. Plus, we plug in n is equal to 2. B times 2 is 2b, and plus c. So we haven't done anything to the c value once again. Now, what are we going to set that equal to? Well, what is s sub 2? S sub 2, if you look at the original sequence, is 11. So there's our second equation. 4a plus 2b plus c is equal to 11. And now the third equation, n is equal to 3. 3 squared is 9. That's where we get the 9 from. B times 3 is 3b. Plus c, we haven't changed 3. And what is that going to be set equal to? Take a look at that and see if you can figure it out. I'll give you a second. Okay, did you say equals 23? If you did, that's the correct answer. So there are our three equations. A plus b plus c is equal to 5. 4a plus 2b plus c is equal to 11. And 9a plus 3b plus c is equal to 23. Now the cool thing about this particular set of what we call simultaneous equations is that the part on the left-hand side of each of the equations is always going to be the same for all quadratic sequences, because those are defined using n's and the original definition of a quadratic sequence above. So that part is always going to be the same. The only thing that will change there are the numbers on the right-hand side. And those are simply the first three elements of the quadratic sequence. So if you write down those 9 terms from the three equations, set them equal to the first 3 terms or first 3 elements of the sequence, you will get the set of simultaneous equations that you need to solve. And what I'm going to call this is the direct approach to solving the problem of quadratic sequences. So here are our 3 equations. And what we're going to do with this, our strategy of solving these, is to get rid of some of the variables and solve for the remaining variables. We call this the method of elimination. Now, to make this problem a little clearer, I'm going to number each of these equations. 1, 2, and 3. So the first step is to eliminate some of the variables is to take equation 3 and subtract from it equation 2. And then I'm going to call this, when I do this, I'm going to call this equation 4. So what is 3 minus 2? Well, or equation 3 minus equation 2. Well, 9a minus 4a is 5a. And 3b minus 2b is equal to just b. And c minus c is 0. So we get rid of that. So we've now eliminated c in one of the, or in 2 of the equations. And then 23 minus 11 is 12. So we write that down. 5a plus b, there's no c, the c has been eliminated, is equal to 12. Okay, great. So now the next idea is, now can we look at that and we say we have an equation, but we have 2 variables. We need to have 2 equations if we have 2 variables. Can we get another equation independent of this one that doesn't have a c in it? And the answer is absolutely. We say subtract equation 2 from, or excuse me, we subtract equation 1 from equation 2, and we will call that equation 5. And so look at equation 2. 4a minus a is equal to 3a. 2b minus b is equal to b. And once again, c minus c is 0. and then 11 minus 5 is 6. So when we write that down, we get 3a plus b is equal to 6. So now we have two equations with two variables. We can solve this problem. So the next strategy is to take equation 5 and subtract from it equation 4. So if we look at the two equations above, we say 3a minus 5a, well, that's going to give us a negative number, negative 2a. Now b minus b, lo and behold, we've now eliminated b. And 6 minus 12 is equal to negative 6. So we write that down. And look at this. We have one variable, one equation. We can solve it. So in this case, we simply divide both sides by negative 2, and we get that a is equal to 3. So we've solved 1/3 of our problem in eliminating the b's and the c's. Okay, let's keep going. Now the next thing we do is we do what's called back substitution. So what we're going to do is we're going to take this value of a and we're going to plug it back into one of the equations and solve for another of the variables. Now we can plug a into either equation 4 or equation 5 and we will get the same answer. For this example, I'm going to plug it back into number 4. Okay. By the way, you could do the same thing with equation 5, and I would suggest you try that as an exercise to make sure that you get the same answer as I get. Okay, so we plug this in. We say 5 times 3, that's what a is equal to, plus b is equal to 12. 15 plus b is equal to 12. And then we subtract 15 from both sides, and we get that b is equal to negative 3. So there's our answer for b. Finally, what we're going to do is we're going to plug these two values into one of the other equations that has a, b, and c in it, and solve for that. And the simplest of them all would be equation number 1. So a plus b plus c is equal to 5. Well, plug in the value for a and b, and we see that 3 minus 3 is 0. We're left with c, and that's equal to 5. So c is equal to 5. There's our 3 equations. So now we have all 3 of the equations, so we can plug that back into our original problem and solve for any value in the sequence. So let's go ahead and check our solution to make sure that we got it correct. So here we go. We plug in the values for a, b, and c, which were 3, negative 3, and 5. And we plug these values in for n is equal to 1, 2, 3, 4, as far as you want to go. You could either use a calculator or you could use a spreadsheet, and you would get the following answers. And if you notice, on the left column, we have 1, 2, 3, 4, 5. And on the right column, we have numbers that happen to coincide with our original quadratic sequence. Now, the problem that you'll most likely encounter on, let's say, homework or even on a test is they will say something like this: given the original sequence, what is the 12th element of that sequence? So all you would do is you would simply plug in 12 for n and, using a calculator, solve for it. And so in this case, s sub 12 is equal to 401. So that would be how you would solve that on a homework problem or on a test. So what is my assessment of this method? Well, one thing that you see in this is that there is some algebra involved in this, and if it's been a while since you've done some algebra, then yeah, you may find it a little bit daunting. However, if you're in high school right now, you're probably familiar with most of these methods. So yeah, the algebras may be a little bit of a drawback, but it's not too bad. But the good news is that you have a 3 by 3 system that's fairly easy to solve. All of the C components have a coefficient of 1, and so it's easy to eliminate those. And the other nice thing is that the left side of all of these equations will be the same no matter what quadratic sequence you try to solve. It's only the right-hand side, the numbers from the sequence, that you have to that will be different. And very simply, you just use the first 3 elements of the um, of the sequence and plug those in for S1, S2, and S3. Of course, the only better way to solve this problem is to get somebody else to do the work for you. Hmm? So next time, what we're going to do is we're going to look at a generic form of the 3 equations. And again, this is the set of simultaneous equations necessary to solve for a quadratic sequence. And what we're going to do is we are going to enter the matrix, aka we're going to look at linear algebra. And as a preview, we're going to take this square matrix. We're going to multiply it by this column vector. We're going to set it equal to this column vector, and we're going to solve the problem easily. See you next time.